So by 1900, it was known that atom is not simple, indivisible particle. Atom was known to contain at least one subatomic particle, and this is the electron identified by J.J. Thomson. So after, though J.J. Thomson, he discovered that electron was present. I think someone was asking last class, what was that particular experiment that he conducted? It was the same that cathode ray experiment that was used for finding out the proton, except that what he did was around the tube there was what you call magnetic field. So that magnetic field, so as a result of which it showed that the particles are negatively charged. Okay, that I mean, we'll in a simple way to say that the particles are negatively charged. They understood because when the cathode ray experiment was conducted, so that means when they passed electricity, cathode rays, it that is it. What it did is it released negatively charged particles, and then what they did is there was an electric field around it, and as a result of which they were able to say that yes, negatively charged particles are formed. So this experiment they have not shown us in our textbook because it is slightly difficult to understand. So we have one magnetic field, second we have the cathode rays, then we have electricity being passed. So that was complicated. So I think that is why our textbook we don't have this particular experiment. But the Goldstein experiment we have because that is little more easier to understand. So before Thomson, he identified an electron. We have a proton being identified by who identified the proton? Anyone?
Goldstein, ma'am.
Goldstein, ma'am.
Goldstein. Goldstein, he
Goldstein,
identified
ma'am.
the Goldstein. Very good. Goldstein identified the proton. So that we will just see. Um, So this Goldstein experiment is also this cathode ray experiment, but there is a little difference there. So now J.J. Thomson, we know that he was a British physicist who was born in Cheetham Hill, a suburb in Manchester, in December 1856. So he was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. So he directed a lab in Cambridge called as Cavendish Lab, and for 35 years, and seven of his assistants, research assistants, they subsequently won the Nobel Prize. So Cambridge Research Lab is a very, very famous lab in UK, and this particular lab, like Oxford, Cambridge, they're known like how we have Indian Institute of Science, like that they're all very reputed old universities. And so in this lab, he worked, his assistants worked, his research assistants worked, and each of their work won the Nobel Prize. So we can imagine how much of work they would have done. So, as we discussed, even before J.J. Thomson, E. Goldstein had discovered in 1886 presence of new radiation in a gas discharge, and he called them as canal rays. So, these rays were positively charged radiation made up of subatomic particles, which he gave the name as protons. So, this he called them as canal rays because they were in the form of canal or channels. And in this experiment, the experiment indicated that they are positive charge. So here, they were called as canal rays because they pass through holes or canals in the cathode. So here, what he had is he had a perforated cathode, and so usually what happens is see perforated cathode, the cathode when they pass electricity, now electrons are released. So this cathode rays, so cathode rays are made up of electrons, so they are released. So what would happen is these rays would go, and here there was a gas present. So these rays would go and hit the gas. So the negative charge would go, and this negative that is the charge or the electrons would go and hit the these atoms of the gas and remove the electrons that are present outside. But these electrons can be easily removed because we know that they don't have much mass. So that would be sort of peeled off. So when the electrons were peeled off, the atoms had a positive charge. So what would happen is they would just go, they would travel as channels. So thus, that is why through this perforation, this positive rays would pass through. So as a result of which he called them as canal rays. And they were, see, once they have positive charge, they will be attracted towards the negative electrode. So they were attracted here and they would pass through the perforations. So thus he called them as, he called them as canal rays. And they have to have positive charge because they are coming towards the cathode. And because there is some hole here, they go passing through that. So thus he said that these rays are different from the cathode rays and they're having a positive charge. So this is a very simple diagram of Goldstein experiment. So it shows that the protons are having positive charge. And this positive charge is different from the negative charge that is produced by the cathode. So thus we have negative charge and positive charged particles. So this we discussed last class. So now can someone read this? We have gone through this, but again, can someone read this?
Can I, ma'am?
Yeah, sure.
Ma'am, can I?
Okay, first I think Madhumita said no. Okay, Madhumita first. Afterwards, who said that next? Somebody said, who is it? I'll write
Ma'am,
down.
Aishwarya.
Okay, Aishwarya. So first Madhumita, please read.
Yes, ma'am. Protons had a charge equal in magnitude to electron but opposite in sign to that of the electron. Its mass approximately 2000 times as that of the electron. Generally, electron is represented as negative and proton is represented as positive. Mass of one proton is taken as 1 unit and its charge is taken as +1. Mass of electron is taken to be negligible and its charge is taken as -1.
Very good. Okay, so what did you understand, Madhumita? So first one, protons had a charge.
Protons had a equal charge in magnitude
to electron.
and to electron, but they are opposite in sign. But the protons are opposite in sign to the electron.
Very good.
The proton's mass is approximately 2000 times of the electron.
Very good.
And electron is generally represented as negative, and proton is represented as positive.
Very good. Then?
And mass of one proton is taken as 1 unit, and its charge is +1, and mass of electron is to be a negligible, and because of that its charge is -1.
Very good. So, so as you the protons have a charge equal in magnitude to the electron, but it is opposite in size. And but the mass is 2000 times as that of an electron. So we consider the mass of an electron to be negligible. That is why it can be easily removed because it doesn't have much mass at all. And electron is represented as negative. So we write it as E minus. Proton is always as positive, P plus. And mass of one proton is taken as 1 unit. And its charge is taken as +1. So the mass, the standard unit for the mass is proton, and it is 1 unit, and charge is taken as 1. And the mass of an electron is taken to be negligible. So we don't consider the mass of electron at all. And its charge is taken as -1. So charge is same, but it is opposite in charge, but it is the same. Proton and electron, they are same. But mass of electron is almost negligible when compared to that of proton. Proton is 2000 times as that of the electron. So this we saw. Now Aishwarya, please read.
Thus, it looks like atoms are made up of electrons and protons mutually balancing their charges. Also, it appears that protons are in the center while electrons can be easily peeled off while protons cannot. Hence, the question was, how are protons and electrons arranged in the atom?
Very good. So what did you understand, Aishwarya? So first point. So thus it looks like.
Thus, it looks like, ma'am, we know that atoms are made up of electrons and protons, and their charge is balancing, ma'am.
Uh,
And electrons are revolving around the nucleus, ma'am, so that protons will not revolve like.
yeah, it looks like protons are in the center because they're having charge. They're heavy, so they are in the center. And whereas electrons are like, they can be easily peeled off. Like we discussed, like an onion peel, onion, how we can easily peel off. Like that, it can be peeled off. While protons, they cannot because they're having mass. So the question was, what is our question now?
How the protons and electrons are arranged in the atoms, ma'am.
Very good. Excellent. So this is the question. So now we know protons are there, electrons are there. One is positively charged, one is negatively charged. The question is, how is it arranged? The atom is the thing that, see, now we know, but those days they didn't know. So they were thinking, how is it arranged? And all of them would do experiments. So we will look at the like we will see how the different models of the structure of an atom. Before that, what are canal rays?
It is positively charged rays, ma'am.
It is positively charged rays. That is, it is
Radiation.
positively charged rays.
Radiation.
Positively charged radiation, or we say rays, and it is made up of protons. But it is, if you want to say simple, it is positively charged rays or radiation. So if an atom contains one electron and one proton, what will be the charge? Will it carry any charge or not?
No,
No,
ma'am.
ma'am.
It is neutral.
It's neutral, ma'am.
It is neutral. Very good. Excellent.
It's neutral, ma'am.
It is neutral. Very good. Now let us look at the structure of an atom. So now who will read? Farhan, can you read?
Yes, ma'am. 4.2, the structure of an atom. We have learned Dalton's atomic theory in chapter 3, which suggested that atoms indivisible and indestructible. But the discovery of two fundamental particles, electrons and protons inside the atom, led to failure of Dalton's atomic theory.
Very good. What did you understand, Farhan?
We have learned about atoms by Dalton's atomic theory, that the atoms are indivisible and indestructible.
Very good. So, but what happened? This is what we learned first.
But the discovery of fundamental particles like electrons and protons inside the atom led to the failure of atomic theory of Dalton's, ma'am.
Very good. So these two particles showed that no, atoms are divisible. They can be convert, like there are still smaller particles present in an atom. So next, who will read this? Who will read?
Can I?
Yeah. So first, I think I saw Pooja. No, Pooja said first. And who is
Yes,
the other
ma'am.
person? Pooja, and the other person is
Mahalakshmi, ma'am.
Mahalakshmi. Okay, first Pooja and then Mahalakshmi. Pooja, please read.
How electrons and protons are arranged within the atom, and following this, many scientists proposed various models. Johnson was the first one to propose a model for the structure of an atom.
Okay. So what did you understand, Pooja?
Ma'am, for this, we understood that it is very necessary to know how electrons and protons arranged in the atom. And for explaining the atom, many scientists propose various atomic models like J.J. Thomson, Rutherford, and Johnson. J.J. Thomson was the first one who proposed the model of the structure of an atom.
Very good. Yeah, J.J. Thomson, I made a mistake. Yeah, he was the first to propose a model for the structure of an atom. Very good. So, like once we know they are made up of electrons or protons, the next question is how is it arranged? So, J.J. Thomson, he suggested the model. So now we'll see the model. So yeah. So Mahalakshmi, no, Mahalakshmi, can you read this? What you can see?
Ma'am, the diagram. Thomson's model of an atom.
So how is the diagram? Can you explain the diagram? So we have a positive sphere, isn't it?
Yes, ma'am, we have a positive sphere. In that positive sphere, the electrons are embedded in it.
Are embedded in that.
Like the nuts, how in watermelon the nuts are embedded in it.
Yeah, correct. Like this, yeah, that is also true. So this is the model. So now you can read this, Mahalakshmi.
Thomson proposed a model of an atom similar to the Christmas pudding. The proton is in the form of a sphere in which electrons are arranged like dry fruits, or we can currents, or we can imagine a watermelon in which the red edible part is the proton and the black seeds present in it are the electrons.
Very good. So what did we understand here, Mahalakshmi? J.J. Thomson.
Ma'am, J.J. Thomson proposed a model which is similar to the structure of atom by comparing it with the Christmas pudding, ma'am. And the sphere is the positively charged proton, ma'am, and the dry fruits are the electrons embedded in it, ma'am.
Correct.
And we can imagine like the watermelon, the red eligible particle is proton, ma'am, and the black seeds are electrons.
Electrons. Very good. So that means the whole, whether it is the whole atom is a proton in which electrons are embedded. So that was his model. Okay. So this model was, the charge was equal. Proton, that whole positive charge and the charge of the electrons, if we take into consideration, his model could say that both the charges are equal. But it could not explain the results that were the results of the experiments conducted by other scientists. So that was the disadvantage. So thus Thomson proposed that an atom consists of a positively charged sphere and the electrons are embedded in it. The negative and positive charges are equal in magnitude. So the atom as a whole is electrically neutral. So this was what he proposed. So although Thomson's model explained that atoms are electrically neutral, the results of the experiment carried out by other scientists could not be explained by this model, as we can see. So now we'll look at Rutherford's model of an atom. Okay, now who will read about Rutherford? Who wants to read? Someone who has not read can read. Pratiksha?
Ma'am, shall I read?
Please.
E. Rutherford, 1871 to 1937, was born at Spring Grove on 30th August 1871. He was known as the father of nuclear physics. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908.
Very good. So he got the he got the Nobel Prize for what discovery, Pratiksha?
Nucleus of an atom.
For the nucleus of an atom with the gold foil experiment. He got Nobel Prize in Chemistry in 1908. Okay. You continue, Pratiksha, this point here.
Ernest Rutherford designed an experiment to know how electrons are arranged within an atom. For this experiment, fast-moving alpha particles were made to fall on a thin gold foil.
Okay. So what did he? So what did you understand, Pratiksha?
To know how the electrons are arranged, he conducted an experiment. In that experiment, he took a thin gold foil and he used alpha particles.
He used fast moving alpha particles. So these are positively charged particles and they're made to fall on a thin gold foil. So this we discussed last class. I mean, I know previous classes. So alpha particles, positively charged particles, they are made to fall on a thin gold foil. So they are double charged helium ions containing 2 protons and 2 neutrons. So they are double charged helium ions containing protons and neutrons. So they don't have electrons. So when they're having only protons and neutrons, they will have a positive charge. So they are having positive charge. So the idea was, if it is the positive charge, it falls on the gold foil. If it is like a structure by Thomson, J.J. Thomson, you're having all over positive charge. This whole sphere is made up of proton. So when it goes and hits the proton, it should come back. But what did he see? He saw that most of the particles were be able to just pass through the gold foil. Only some were getting deflected and few were like coming back, very few. So thus we see that there is a scattering of alpha particles by a gold foil. So they are just going through, and a few places we are having deflection. So this experiment showed that J.J. Thomson's model could not be really accepted. So Rutherford, he was able to say that, because here we can see that only if you see so many, if you can see so many rays, only one ray is coming back 180 degrees, it is going and coming back. But whereas the rest of the places, it is, we can see that it is, there is space for the rays to pass through. So this indicates that only in some place you are having a positive charge present, and that is deflecting the rays back. So based on, so let us again just go through what experiment he had conducted. So Rutherford selected a gold foil because he wanted as thin a layer as possible. This gold foil was about 1000 atoms thick. So as we discussed, alpha particles are doubly charged helium ions. Since they have a mass of 4 units, the fast moving alpha particles have a considerable amount of energy. So they are having 4 units, that is, they are double charged helium ions, and so they're having 2 protons, 2 neutrons. So as a result of which they have a lot of energy, they can just pass through. Okay, so can someone read this? Somebody can try.
Ma'am,
Yeah, read.
I was that proportion particles would be deflected by the subatomic particles in the gold. Particles were much heavier than the proton.
Yeah, so what did you understand? He expected that alpha particles would be deflected by the subatomic particles in the gold atoms, because if the structure of Thomson is, it is proton, means this is positive, this is positive. So he said that it should get deflected, it should just come back. And he expected that alpha particles were much heavier than the protons. He did not expect to see large deflection. Actually, since he expected that this alpha particle, since it is made up of protons and then there is neutrons, like they're very heavy particles. So what he thought is, because of they are heavy, they're fast moving, to some extent they will get deflected. So that is what he thought. Okay, but what happened? So he saw that he got unexpected results. So we have discussed that. So who will read this?
Ma'am, can I?
Yeah, Anjali.
Can I?
Yeah, Anjali first. Then who's the other
Yes,
person?
ma'am.
Okay,
Sanjana, ma'am.
Sanjana. First Anjali, then Sanjana. So
But
Anjali,
the
please.
alpha particle scattering experiments give totally unaccepted results. The following observations were made. Observation first. Most of the fast-moving alpha particles passed straight through the gold foil. Second observation. Some of the alpha particles were deflected by the foil by small angles. Third observation. Surprisingly, one out of every 12,000 particles appear to rebound.
Very good. What did you understand from this? So the alpha particle scattering experiment. What happened?
The alpha partic some of the alpha particles are uh, passed straightly, ma'am, and some of the alpha particles are deflected, and very few alpha particles are rebound.
Rebounding. So they're going straight and coming back. See, actually, what he thought, he thought that alpha particles are positively charged, they're heavy, so they will go hit positive charge if it is as Thomson said, and they'll get deflected slightly because they're very heavy particles. That is what he thought. But he saw that most of the particles passed straight through the gold foil. Some of the particles were deflected by small angles, and some, that is 1 out of every 12,000 particles, appear to rebound. So they go straight and they come back. Very good. So, so when it is like he says in words of Rutherford, this result was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. So see, actually the alpha particle, they're heavy, they're fast moving. So there should be, like, that he didn't expect much deflection because these fellows are heavy. But he's seeing that they're coming back, rebounding back. So he said that if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. So he didn't expect it to come back, rebound fully, because they are moving fast and they are heavy. So this experiment we discussed, no, like if a child is sitting in front of a wall with his eyes closed, if he is throwing stones on the wall, he will hear sound each time the stone hits the wall. But if the child is closing his eyes and throwing stones on a barbed wire fence is like this, there'll be a number of wires present with a lot of gap. Then only some stones will hit the fence, and the sound will not be heard most of the time. Is because there is a gap. Through the gap, it will go. So it is like that. So if it is so what this experiment showed that there was gap. Only few stones were able to hit something that is present in the atom, and so as a result of which Thomson's model could not be accepted. So this we discussed. So following a similar reasoning, Rutherford, he concluded from the alpha particle scattering experiment that, so what did he conclude? Most of the space inside the atom is empty because most of the alpha particles pass through the gold foil without getting deflected. So that means there's a lot of space within the that particular atom that is the gold atom. Very few particles were deflected from their path, indicating that positive charge of the atom occupies very little space. Then a very small fraction of the alpha particles were deflected by 180 degrees, indicating that all the positive charge and the mass of the gold atom were concentrated in a very small volume within the atom. So only in a very small volume within the atom, all the positive charge and the mass of the gold atom is present. So this was his conclusion from his experiment. So he did a lot of experiments, and from all his data, he calculated that the radius of the nucleus is about 10 to the power of 5 times less than the radius of the atom. So 10 to the power of 5 times less than the radius of the atom means how much it will be? 10 to the power of 5 means, we discussed now, 10 into 10 into 10, 5 times. So it will be units, tens, 100,000.
1 lakh.
1 lakh times, yeah. It is 1 lakh times less than the radius of the atom. So it's so small. See, its radius is 1 lakh times less than the radius of an atom. So based on that, so on the basis of his experiments, Rutherford put forward the nuclear model of an atom, which had the following features. So he said that there is a positively charged center in the atom called as a nucleus, and nearly all the mass of an atom resides in the nucleus. And he said that the electrons revolves around the nucleus in circular paths. And he said that the size of the nucleus is very small as compared to the size of the atom. So this is what he said. So in the nucleus, we are having all the charge and all the mass. And the size is very small when compared to the size of the atom. But there is one drawback of Rutherford's model of the atom. Okay, now who will read this?
Mummy.
Yeah, Sanjana. Yeah, right.
Drawbacks of Rutherford's model of the atom. The revolution of the electron in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. We know that atoms are quite stable.
Very good. So what did you understand, Sanjana? The drawback? So what was the drawback? The revolution of?
The revolution of the electron is in circular orbit, ma'am.
Yeah, it is not expected to be stable. No, why it is not expected to be stable? Because when it is circulating, it will undergo acceleration. It will go fast. Acceleration. So during acceleration, what will happen? These particles
charged particles radiate energy, ma'am.
Very good. Yeah.
So the revolving electron lose their energy and they fall into nucleus, ma'am.
It will fall into the nucleus. So if this were so, what if it falls into the nucleus? Atoms should be highly unstable. But we know that matter, it is quite stable. Whatever matter we see, it exists in the, whatever we see is all stable, no? So thus, it shows that Rutherford's model, there is some drawback, like this revolution of electron, as suggested by Rutherford, seems to show that it'll revolve, it'll lose energy, it'll fall, and it'll make the atom unstable. But that is not so. So this was only drawback of Rutherford's model of atom. Very good. So now then Bohr came out with Bohr's model of an atom to offer a solution that is to overcome the objections that were there in the Rutherford's model. Okay, so in order to overcome the objections raised against Rutherford's model of an atom, Niels Bohr put forward the following postulates about the model of an atom. See, whenever they say postulates, you can see always they'll say postulate is because they really will not, they will just put forward. They will not really have a proof. It will be more of a theory, like. So they will put forward and then they will try to explain. They'll do experiments and then they will postulate. They'll say it is like this, it is like this. So all of them will do experiments and then they'll come to a conclusion. So sometimes it will be accepted, it will be proven to be right. Sometimes we see that there may, it may be not true, like how Dalton's model was. Okay, what is Niels Bohr's postulates? Anyone wants to read these 2 points, important points? Naveen wants to try. That time it was not clear, no, the sound was not clear. Some disturbance was there. So Naveen, you want to try? See, all of you know, you just try. We see what our aim is to understand. Our aim is to learn. So sometimes we are right, sometimes we are wrong. It is okay. But the most important thing is all of us must attempt. So that way what will happen is, we will understand better. And when we make mistakes, we'll understand faster actually. Okay. So Naveen, you should try. Can you try? You only read, no? The that Rutherford's model.
No, ma'am.
Oh, okay. You read, no? Okay. I thought that name comes here. Okay. Now you can try this to read this.
Yes, ma'am. In order to overcome the objections raised against Rutherford's model of the atom, Niels Bohr put forward the following postulates about the model of an atom. First one, only certain special orbits known as discrete orbits of electrons are allowed inside the atom. While revolving in discrete orbits, the electrons do not radiate energy.
Very good. Excellent. So what are these 2 points? One is?
In atom, the special orbit is known as discrete orbit of electrons, ma'am. They allowed to they are in the inside the atom.
Very good. Excellent.
And the revolving discrete orbit the electrons do not radiate energy.
Very good. So that means in the atom there are special orbits known as discrete orbits. So in these special orbits in which are allowed inside the atom, and in this the electrons are present. So in special region the electrons are present, and while revolving in these discrete orbits, the electrons do not radiate energy. So they do not lose the energy, and then they do not fall into the nucleus. So they can continue to that is revolve around the nucleus. So that is what was proposed by Bohr. And these discrete orbits are also called as shells, are called energy levels. So they are called as energy levels, and energy levels in an atom are shown in this figure. So there is nucleus, and then you are having K shell, L shell, M shell, N shell, or K shell is also called as that is a number 1, because it is. So you have nucleus, and you have the first shell 1, second shell, L is also called as 2, and M shell and N shell. And why this K shell, why they it got the name K, was when the scientist did the experiment, he found that it had more energy than the X-rays. So he called this as kapha, the Greek word kapha, so K. And L is having less energy, lambda. So that he named as K, L, M and N. So these orbits or shells are represented by the letters K, L, M and N, or the numbers 1, 2, 3, 4. So this is, and in these orbits the electrons are present. So when they are present in these electrons, and they are revolving in these electrons, they do not lose their energy, and they can continue to be go around the nucleus. So who will read about Niels Bohr? So after Sanjana, Naveen, next who will read? So Aishwarya, can you read?
Yes, ma'am. Okay, ma'am. Niels Bohr was born in Copenhagen on 7th October 1885. He was appointed professor of physics at Copenhagen University in 1960. He got the Nobel Prize for his work on the structure of atom in 1922. Among Professor Bohr's numerous writings, 3 appearing as books are: first one, The Theory of Spectra and Atomic Constitution; second one, Atomic Theory; and third one, The Description of Nature.
Very good. So he got the Nobel Prize for his work on the Nobel Prize for his work on the structure of atom. First, so he got the Nobel Prize in 1992. So here, uncle wants to put forward some explanation on the structure of atom. Okay.
Hi children, good evening.
Good evening, sir.
Good evening, sir. Good evening, sir. Good evening, sir.
Good evening, good evening. I was just overhearing what madam was teaching. So I thought I would give some, this is a difficult concept. Why the shells are so chosen, energy levels are so chosen that it isn't the electrons don't fall into the center core. Why they are rotating around in that orbit, particular orbit. Have you ever thought about it?
Yes, sir.
Yes, sir.
Yes, sir.
ಯಾಕೆ ಬೀಳ್ತಾ ಇಲ್ಲ ಒಳಗೆ? ಓಕೆ. ಈಗ
Sir,
ಒಂದು
opposite energies.
ಈಗ ಒಂದು ಚೈನ್ ಅಲ್ಲಿ ಒಂದು ಥ್ರೆಡ್ ಅಲ್ಲಿ ಪುಟ್ ಎ ವೆಯ್ಟ್ ಅಂಡ್ ರೊಟೇಟೆಡ್ ಅರೌಂಡ್ ದ ಸೆಂಟರ್. ನೀವು ನೋಡ್ತೀರಲ್ಲ ಹಿಂಗೆ ರೊಟೇಟ್ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ? ಒಂದು ಕಲ್ಲು ಒಂದು ಥ್ರೆಡ್ ಅಲ್ಲಿ ಇದು ಮಾಡಿ ಟೈ ಮಾಡ್ಕೊಂಡು ಹಿಂಗೆ ರೊಟೇಟ್ ಮಾಡಿ ಏನಾಗುತ್ತೆ? ಅದು ಹೆಂಗೆ ರೊಟೇಟ್ ಆಗುತ್ತೆ?
Circular path, sir.
In a circular path, sir.
Circular path. So why is it rotating? Because you are applying some force at the thread with your finger, and the energy level is passed. Energy is passed to the stone, and stone assumes kinetic energy, and the kinetic energy is divided into two directions. One is centrifugal and centripetal forces, and these two forces will get equal and opposite, so it becomes stable. Stable means it rotates, but it doesn't accelerate. So it keeps on rotating. Acceleration is that because there is change of direction. So when there is a change in direction, acceleration will be angular acceleration helteve. So either in the actual atom level, in the subatomic level, you can imagine this as a force of attraction between the proton and the electron. That creates a force between the electron and the proton, the center, the core. Okay, and this orbit is so calibrated that these fellows will go on rotating without losing its energy levels. If it loses the energy level, it will fall into this, or it can go to the next. If it is gaining more energy, it will fly away. Correct? Now, ಈಗ ಸ್ಪೇಸ್ ಕ್ರಾಫ್ಟ್ ಬಿಡ್ತೀವಿ, ಈಗ ISRO ಎಲ್ಲ ಸ್ಪೇಸ್ ಕ್ರಾಫ್ಟ್ ಬಿಡ್ತಾರಲ್ಲ, ಏನಾಗುತ್ತೆ ಸ್ಪೇಸ್ ಕ್ರಾಫ್ಟ್ ಅಲ್ಲಿ ರಾಕೆಟ್ ಬಿಡುವಾಗ ಹೇಗೆ ಅದು ಎರ್ತ್ ಸೆಂಟರ್ ಆಫ್ ಎರ್ತ್ ಅಟ್ರಾಕ್ಟಿವ್ ಲೆವೆಲ್ ಫೋರ್ಸ್ ಅಲ್ಲಿ ಎರ್ತ್ ಅಟ್ರಾಕ್ಟಿವ್ ಒಂದು ಮೇಘಲೆ ಇದೆ, ಅದು ಬಿಟ್ಟು ಹೊರಗಡೆ ಸ್ಪೇಸ್ಗೆ ಹೋಗ್ಬೇಕಂದ್ರೆ ಅದು ಇಟ್ ಹ್ಯಾಸ್ ಟು ಗೈನ್ ಇನಫ್ ಸ್ಪೀಡ್ ಅಟ್ ಎ ಪರ್ಟಿಕ್ಯುಲರ್ ಆಂಗಲ್. ಆ ಆಂಗಲ್ ಬಂದ್ರೆ, ಆಂಗಲ್ ಅಂಡ್ ಸ್ಪೀಡ್ ಬಂದ್ರೆ ಅದು it can go to the next level and goes to space. Otherwise the earth will be pulling it by the force of magnetic field. So by the force of attraction between these two, there will be a field, attractive field. So this particular energy levels, that is called energy level. At a particular level, what is the energy level of the electrons or the rotating body? And if the electrons or the body wants to find an equilibrium state, it will automatically fall into a particular distance at which it will be stable. And this is called the levels, the M shell alla heltivalla. This is the level in which the electrons move around the center. ಅದಕ್ಕೆ ಒಂದು ಎಲ್ಲ ಎನರ್ಜಿ ಲೆವೆಲ್ ಹೇಳ್ತೇವೆ. ಆ ಎನರ್ಜಿ ಲೆವೆಲ್ ಅಲ್ಲಿ ಆರ್ಬಿಟ್ ಅಲ್ಲಿ ಓಡ್ತಾ ಇರ್ತದೆ. ಸೊ ಇಟ್ ಇಸ್ ಗಾಟ್ ಅ ಡಿಸ್ಟೆನ್ಸ್ ಎಲ್ಲ ವೆರಿ ಅಕ್ಯುರೇಟ್ಲಿ ಪ್ರೆಡಿಕ್ಟ್ ಮಾಡಬಹುದು ಒಂದೊಂದು ಶೆಲ್. ಬಟ್ ದ ಡಿಸ್ಟೆನ್ಸ್ ಇನ್ ಸ್ಪೈಟ್ ಆಫ್ ದ ಡಿಸ್ಟೆನ್ಸ್ ಇಟ್ ಇಸ್ ಬೆಟರ್ ಡಿಫೈನ್ಡ್ ಆಸ್ ಎನರ್ಜಿ ಲೆವೆಲ್ಸ್. ಆ ಎನರ್ಜಿ ಲೆವೆಲ್ ಅಲ್ಲಿ ಹಂಗೆ ಓಡ್ತಾ ಇರ್ತದೆ. ಅರ್ಥ ಆಯ್ತಾ? ಸ್ವಲ್ಪ ಎಲ್ಲ ಕನ್ಫ್ಯೂಸ್ ಮಾಡ್ಬಿಟ್ರ? ಅರ್ಥ ಆಯ್ತಾ?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
Yes, sir.
very good, very good, very good. Okay, I will give it to madam. Huh?
Thank you. Okay.
Excuse me, ma'am.
Yeah. Yes.
Ma'am, why do electrons do not radiate while moving in these discrete orbits?
Why do they not radiate energy? Yeah. Why do they not radiate energy when they're moving in these discrete orbits?
Radiate
Yes,
energy. What do you mean by radiation?
Emitting
Radiation.
of rays. Emission of rays.
Or why lose? Or that is one way of saying. Or why do they not lose energy when they go on moving? They'll start losing energy after some time.
See, the energy can be present in multiple in the magnetic field, magnetism, electric field, magnetic field, or light. Light is also a form of energy. But in this case, the lights basically is made of photons. It's a wave of photons. That's called wave theory. Now, the energy of the electrons are present in because its mass is so low. It has a kinetic energy and the kinetic energy. And because of the force of attraction between the two, the center core and the electron is present, is an attractive force. And it has to be stable when there is a centripetal force and centrifugal forces. You know, you know what is centripetal force? Centrifugal forces are towards the center. Centripetal is away from the center. So when these two forces are equal, the body will be in a stable place. Now, everything is due to magnetic attraction, magnetic field.
So that energy level is because of that. So when they're going,
energy level is due to magnetic field. The whole universe is because of magnetism.
See now, if
okay. The whole universe is holding together because of magnetic field. It happens to the micro level. It happens in the macro level, super macro level between planets and interplanets. That is how they exist and then rotate and our solar system. Why is it rotating so accurately? The magnetic field is so defined very well that it is stable. ಇಲ್ಲಾಂದ್ರೆ ಅರ್ಥ ಓಡೋಗ್ಬಿಡುತ್ತೆ. ಎರ್ತ್ ಹೆಂಗೆ ಹೋಗುತ್ತೆ, ಸನ್ ಹಂಗೆ ಹೋಗ್ಬಿಡುತ್ತೆ.
Okay, sir. Thank you.
ರೇಡಿಯೇಷನ್ ಬರಲ್ಲ ಅದಕ್ಕೆ. ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ರೇಡಿಯೇಷನ್ ಬರಲ್ಲ.
ಅದರಲ್ಲಿ ಕೊಟ್ಟು ಇವರಿಗೆ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದಾಗ they have told they lose energy and they'll the force model.
If they lose energy, it will fall into the it will fall.
Why anta question adike
naturally. If it loses energy, it will go to the lower level of the shell, lower shells.
So why it is not, when it is in that particular orbit, why it is not losing the energy in a particular orbit?
That's what I was telling you. That orbit is a stable orbit for the body to rotate.
For that particular, okay, for the two electrons.
Because at that energy level, at that orbit, these forces, attractive forces and repelling forces, are equal.
Okay.
So it becomes stable.
Okay. So students, can we like
in the universe, you have heard about black hole?
Yes, sir.
Yes, sir.
What do you know about black hole? One of you answer.
Danaya, I think I saw his name first. Danaya, can you answer?
Yes, sir. Hole has a more gravity.
Huh?
Black hole is a more gravity, sir.
Okay, I will explain. Our sun, sun is burning, is emitting so much energy, and at one point, the sun will become empty because there won't be any more fuel left. So what happens is it will burn up, and it will expand. Once it is burns up, it will expand. It won't be compact anymore. It will expand, and when it expands, it will engulf the other planets nearby. Earth will be engulfed. Mars will be engulfed. So it becomes engulfed body. It will gain mass, and then it becomes a super body with so much energy. it will engulf all the other things. That is a black hole. Even the light photons, photon energy is also engulfed. So that is why it is looking black. Actually, it is not black. Everything is drawn inside. So the light doesn't come out. That is why it is called black hole. Through radiometry, they cannot find out a black hole. It's very difficult. So what I was trying to say is, what was your question?
Sir, in the discrete orbits, why does the electrons do not lose or gain energy?
That I answered, because that is a stable equilibrium orbits where it cannot lose or gain.
Now I have a doubt. Okay, is it like now we have sun and we have all the planets revolving around the sun? So can we consider sun to be a nucleus and all the planets?
Yeah, you can imagine that way.
Discrete orbits in which all the planets are all revolving.
You can imagine
that. That's a very nice thing. I think that makes our life easy, isn't it, students? We can think like that.
See, when the sun erupted, so many millions of years back, or billions of years back, or trillions of years back, what happened is it erupted. It gave its it has so much energy, it erupted. So some of the mass went out and took a stable position, stable orbits, and that is the stable orbit in which it is rotating. Why it is not falling inside the sun? Why Earth is not falling? It is so precisely it is moving, because it is if it is losing energy, it will fall into the sun. It will be we will be losing the distances.
We learned actually.
So that is the universal truth, and same thing is applied in the atom also. This postulation, nobody has seen an atom electron rotating around the nucleus. Nobody has seen it. These are all postulates, and there are some other theories are there. Why it is rotating? There are spins. It is not just rotating; it is spinning. So spinning also has an energy. Why it is spinning, and what is the spin rate? There is called clockwise spin and anti-clockwise spins. So any body which spins has got a energy, has got an angular velocities, and angular velocity will create the energy. Okay, and they try to tend to become stable, and that stable locus is the orbit. And that is why it is not falling inside the inside your center core. But if you disturb by adding heat or by adding some attraction magnetic field, then it can gain energy. Then the levels will change. The orbits, it can go to some other levels. Or if you cool it down, probably cool it down, probably it will slip the orbits. It is possible. And same thing will happen to the Earth also. If there is an asteroid hitting the Earth, it can change the position. So much energy is falling on the Earth, and can change the direction also. It can change the orbital path.
Oh, okay.
It has happened. Or if you are creating a nuclear explosion, what happens? So much of force you release, the Earth can change its path. Okay.
Okay, very interesting, no, students?
I just want you to ponder over. They're all very interesting, and every time you look at the sky, this is happening every second, every millisecond, every trillionth of a second, it is happening.
And also the point, they studied plasma, sun, as an example of the fourth state of matter called plasma.
And these are all taught in astrophysics. And those who are interested in this can go to astrophysics.
And this is sun plasma is because of fusion, no, not fission. Fusion.
It's a fusion reaction. Okay, right.
Okay, students, then I think, this questions we will just go through. So on the basis of Thomson's model of an atom, explain how the atom is neutral as a whole. So now on the basis of Rutherford's model of an atom, which subatomic particles is present in the nucleus of an atom? What is present in the nucleus of an atom?
Proton, ma'am.
All of you must should. What is it?
Proton.
Positively charged proton.
Proton is present in the center. Draw a sketch of Bohr's model of an atom with the 3 shells. You can all just try. And see, the more you practice, it will make it more and more, easy for you to remember. So what do you think would be the observation if the alpha particle scattering experiment is carried out using a foil of a metal other than gold? Theoretically,
There will be no change.
there should not be any change.
It remains same, ma'am.
It remains the same. Except that, can we get a thin sheet, a thin foil like from other metals like iron is the question. Or does it have, say, aluminum may not have the strength, but theoretically, yes, it should be the same. Okay, students. So next we will look at, that is, we discuss this neutrons. 1932, Chadwick discovered another subatomic particle which had no charge and mass equal to that of the proton. And this subatomic particle was called as neutron. So this is having mass equal to that of proton. And so this neutrons are present in the nucleus of atoms except hydrogen. Hydrogen is having only a proton in the nucleus. In general, neutrons are represented by N. Therefore, the mass of an atom is a sum of the masses of neutron and proton present in the nucleus. So nucleus contains neutrons, protons. This together forms the mass of an atom. So when you say atomic mass is the sum of mass of neutron and proton. Atomic mass is proton plus neutron. Atomic number is the mass of only the proton. Atomic number is only proton. Atomic mass is neutron plus proton. Okay, so then we looked at the different structures. So we will continue in the next class, and then we'll look at we'll try to understand the valency. We have discussed, again, we will look at more about valency, again discuss about atomic number and atomic mass. So today we will just end with these questions. So name the 3 subatomic particles of an atom. All of you must tell me. What are the 3 subatomic particles of an atom? Very good. So protons, electrons, and neutrons. So these are the 3 subatomic particles of an atom. Then next question. Helium atom has an atomic mass of 4 units and 2 protons.
2, ma'am.
Yeah, very good.
2, ma'am.
2. Very good. 4 minus 2, 2. So how much neutrons does it have? It has 2. Very good. So you're all clear with this. So next class, we will just go through that how orbits, the electrons are distributed in the orbits little more, and then we will look at some examples and then go forward to valency. Okay, students? Bye.